Okay, so following on from our data set, which is the population of cities in England, here was the original data. Okay, so top rank is London with 8.2 million. This is a 2001 census, and you can see the different cities and their population sizes. And it turns out that power models are very good models to fit population against rank. So when we go back to our data set here, we get this beautiful graph, and there's the power model that fits perfectly through it. And so it kind of makes sense that we go straight for technology because we're living in a modern age. And of course, the fit for the power model is a very good fit. We worked out an R-squared value. It was a very good coefficient of determination. And of course, any time we kind of see data that looks like this, or maybe like this, we may have a justification for the power model. Okay, power model is quite close to the exponential model, but exponential model, we expect some kind of percentage increase or decrease. With a power model, it might not be the case. So what we're going to do is we're going to take a step back to the 18th century. Obviously, modern technology will find us the perfect values for B and A that give the best fit line. Now, of course, the best fit line might not go through all the data points, but it's called a best fit line for a reason, right? And the best values for A and B will be found automatically by a computer or your calculator. But back in the 18th century, of course, this technology did not exist. But it was still possible to find the best A and B values to make this kind of model. But what happened, of course, back in the day was the only technology available to them was technology by hand. And so what they did was take the data and make it look linear, right? And if they could make the data look linear, then they could fit a straight line through it. Now, even in the 18th century, they could find the perfect values for M and C to make the line of best fit. And this was just a long process by hand. But it was possible to find a line of best fit if it was linear. They also could actually take logarithms of any number. So they could actually make big numbers small by taking the logarithm of that number. So we're actually going to use that technique to change our data that looks like this into data that looks actually quite linear. All right, so first of all, let's go back to our TI-NSpire. And on our TI-NSpire, what I'm going to do is, back to the spreadsheet, I'm actually going to take the logarithm of both data sets. So in here, I'm going to put ln for log of the rank, and put natural log of the population in here. And I'm going to put a formula in here, equals natural log of rank. And in here, I'm going to put a formula equals natural log of pop. I'm going to overwrite. Beautiful. And now in our graph, we are going to plot not the rank, but the natural log, ln of rank. You see already it's kind of, I'll just get rid of this previous graph. I think I can get rid of it. So already it's gone from super steeply curved to slightly curved, but if I hit the natural log of population, can you see that? This now, we've made the data go from, pretty much steep down into a more linear. So now I'm going to go ahead and go menu, analyze, regression. I'm going to put a linear model on here. Now look at the linear model. Okay, so of course there's a gradient times by the x variable plus the y-intercept, 15.7, and that gives us the y variable. Okay, so we're going to take this equation and we're going to write it down on our iPad, and then we're going to go and play with it. So here's the iPad. Here's the next page. So let's go ahead and transfer that equation over to the iPad. So the y value of a straight line is equal to negative 1.3507 times by the x value, and that is plus 15.744. Okay, we'll do 1, 2, 3, 4, 5 sig figs. All right, so what we've got to think now is, well, actually the y and the x variable, what did we actually plot on the y-axis and what do we actually plot on the x-axis? Well, I think you probably remember that actually on the y-axis we plotted the natural log of the population size. And on the x-axis we plotted the natural log of the rank R. So actually the equation that we've got is this one. Okay, and that's pretty much it. This is the kind of linear version of, and we'll just go back to our calculator again. It's the linear version of this model where we had the rank against the population and we had the menu, analyze, regression, power. Okay, so let's write down the power model, and the power model was P equals 6876347. We'll leave all the decimal places off. X to the negative 1.3507. And I'll just replace the x because the x was the rank. Okay, so these are actually two equivalent equations linking population with rank.